everybody. This episode, I'll be speaking with Jaime Sevilla. Jaime is the director of Epoch AI, an organization that researches the future trajectory of AI. In this conversation, we use the term flop a lot. Flop is short for floating point operation, which just means a computer multiplying or adding two numbers together. It's a measure of how much computation is being done. Links to what we're discussing are available in the description, and you can read a transcript at xrp.net. Well, Jaime, welcome to Excerpt.
Thank you for having me here.
So you study just AI, how it's progressing. At a high level, for people who have been living under a rock, how's AI doing? How's it progressing?
It's going pretty fast, Daniel. I think that right now the two things that you need to take into account when you're thinking about AI is like how fast inputs into AI are going and how fast outputs are going, like how much is being achieved. In terms of inputs, like the progress is exponential. Like the amount of compute that's being used to train modern machine learning systems is increasing at a staggering pace, like nearly multiplying by a factor of 4 every year. In terms of the outputs, we also have seen some dramatic advances. This is a bit harder to quantify naturally, but if you look at where image generation was 4 years ago and you compare it with today, like today we have like photorealistic image generation, whereas before it was like these blobs that you could make that were like vaguely related to the text that you were entering. And in text, we have also seen like these very dramatic advances where like now I use and I suppose that many in the audience will be using ChatGPT daily to help them with their tasks and coding.
Yeah, if people are interested in kind of just statistics about what's going on with AI, one thing I really recommend they do is you have this dashboard on your website. Is it called dashboard or is it called trends or something? I forget what.
Yeah, we call it the trends dashboard.
Trends dashboard. Okay, there. So that's one thing that people can use to get a handle on what's going on. One kind of question I have in this domain is, so I have an Anki deck, right? So it's basically a deck of flashcards. And sometimes it shows me a flashcard, and I say like whether I got the answer right, and then it shows it to me like very soon if I got it wrong, or like some period of time later if I got it right. Anyway, in this deck, I have just some flashcards of like, how big are various like books or whatever, just in terms of number of words to give me a sense of like word counts. I also have, how many floating point operations were used in training GPT-3. I'm wondering if somebody wants to have just a good quantitative sense of what's going on in AI, what should they put in their flashcard deck?
Yeah, the two main things you need to put in your Anki deck is the one is the number I already gave you, which is the increase in training compute per year. Like right now, one of the best predictors that we have of performance is the scale of the models. And the best way of quantifying the scale we have found out to be the amount of computation that's being used to train the models in terms of the number of floating point operations that are performed during training. This is increasing right now for notable machine learning systems at a pace of like 4x per year. And if you look at models at the very frontier, you also find like a similar rate of scaling. So I would recommend you put that number and together, but that's not the whole picture because alongside with the compute, there is also improvements that we have seen to architectures, ways of training, to all these different techniques and scientific innovations that allows you to better use the compute that you have to train a more capable system. So all of that we usually refer to with the name of algorithmic improvements. And we had this cool paper where we tried to quantify like, okay, what's been the rate of algorithmic improvement in language models in particular. And what we found is that roughly the pace was that the amount of resources that you need, the amount of compute that you need to reach a certain amount of performance was decreasing at a rate of about 3x per year, roughly. And actually have like a fun anecdote about this, which is just this week, Karpathy released like he's been working on this project, right, where he's trying to retrain GPT-2 using modern advances in architectures at like a much cheaper scale.
Right.
And he shared like this number, which is like, well, like we don't know exactly like how much GPT-2 costed when it came out in 2019, but I estimate that it costed like around like $100,000 to train. But with all these techniques that he has applied, like he trained a GPT-2 equivalent model for about like $700.
Wow, that's a lot cheaper. Yeah, I mean, okay, there are a few things. Yeah, let me just get into some of this. So, in terms of compute, right? This is going off this thing. I think it was called training compute of frontier AI models grows by 4 to 5x per year. Very descriptive title by yourself and Edu Roldan. How like growing the amount of computation used in training AI models by 4 to 5x per year? That seems kind of insane. Like, is there I don't know if you know the answer to this question. Is there anywhere else in the economy where like the inputs we're putting into some problem are like growing that fast that isn't just like some like tiny, random minuscule thing?
Yeah, this is an excellent question to have. I don't have any real examples of the top of my mind, but it will definitely be interesting to hear if there are any analogs to this.
Yeah, yeah. I guess that's if any listeners are have some sort of quantitative econ bent, I'd love to know the answer. So like, yeah, how did you figure that out?
Pretty simple. So this all traces back to even before Epoch. I was a bit frustrated with like the state of the art in talking about AI. The state of the art on in talking about how AI is going, because people were trying to be like not very quantitative about it. Whereas where we were already living in this world where we already had the systems, we could already do like a more systematic study of
Hmm.
what's happening. I actually started together with my now colleague Pablo Villalobos, like writing down information of like, okay, like this is 100 important papers in machine learning. This is like the amount of resources that were used to train the models. This is the size of the models and such and such. And this project has continued up until now. And now at Epoch, we have taken on the mission of keeping this database updated of notable machine learning models throughout history, and annotating like how much compute was used to train these models. This is at many points is like is a lot of there's a lot of guesswork involved. Like people don't usually report these numbers very straightforwardly, so we need to do a bit of detective work in figuring out like, all right, like in which kind of cluster was this model trained, like which model of GPUs did it use, for how long was it trained, and from there make a sensible estimate of the amount of computation that was used to train the model.
Sure. How well are you able to do this? So one thing I'm thinking of is my understanding is that OpenAI basically doesn't tell anyone how it made GPT-4. Like I think I'm not even sure that they've confirmed that it's like using transformer architecture at all. Um in a case like that where they're just not releasing seemingly any information, like how much can you do to figure out like how much they trained it on?
Yeah, so the answer here is, well, some information gets leaked. Eventually, there's like some unconfirmed rumors, and sometimes you can use them to paint like an approximate picture of what is happening. You can also look at the performance of the model and compare it with the performance of the model of like for which you actually know the compute, to try to
Hmm.
get an idea of like, okay, how large do we think the model is. Like this is obviously not perfect, and this is the now as a situation that's been increasingly more common for the last couple of years, in which like the labs that are the frontier of capabilities like are more reluctant to share details about their models. This is something that I'm a bit sad about. I think that the world would be a better place if we were more public on like the amount of resources that's being used to train the systems. Obviously, this has like some implications, and this is useful information for your competitors to some extent. So it's like understandable to a point that labs are like reluctant to share this information. But given the stakes of like the development of this technology, like I would be happy if we had like this collective information on like how many resources do you need to train a model with like a certain amount of capabilities.
Sure. I mean, so okay, one possibility is leaks. I sort of see how that could be useful for something like GPT-4. In the case of these frontier models, presumably the thing that makes them frontier models is for at least some of them, there are just no comparable models that that you can say, oh, GPT-4 is about as good as this thing, and I know how much computation was used in training that thing. So, like, can you do anything there, or is it just leaks?
So For example, let's walk through how we did the estimate of for the compute of the Gemini Ultra model. So for the Gemini Ultra model, like we didn't have the full details of how it was trained, but we had like some reasonable guesses about the amount of resources that Google has at its disposal. And from there, we made like an estimate based on like, okay, like we think they have like this many TPUs. We think that it was trained for like this long, and this gives us like an anchor estimate of that.
Hmm.
The other thing that we did is together with the model, like they released results on like series of benchmarks. Like this is quite common, right?
Hmm.
So what we did is look at each of these benchmarks, and then for these benchmarks, like we already had previous estimates of like the performance that other models got on these benchmarks and the amount of compute that they had. And this allows us to paint like this picture of like this is a rough extrapolation of like if you were to increase the scale of these models, like which performance would we expect you to achieve
Right.
in that. From there, we kind of like backed out like, okay, like given that Gemini Ultra achieved like this performance in this benchmark, like what the scale did we expect it to have? And then like what we found is that these two ways of producing an estimate, like the hardware based one and the benchmark based one, like they look like kind of similar. So that kind of gave us confidence in saying like, well, this is in the end a guess, and we have like huge uncertainty. This could be off by a factor of 5, but it seems like somewhat reasonable to say that Gemini Ultra was trained with around like let's say 5 10 to the 25 flop.
Okay, this is kind of a tangent, but like I remember, I think like a week or so or two ago, I was looking at your trends dashboard. Uh, I think because I was going to suggest that some other people look at it. And I had a look at I had a look at this number, like 5 by 10 to the 25. And also, I was looking at this thing, this guy called Daniel Cocatello wrote in 20, it was something like 2021. It was like just a vignette for what he thought the next like 4 or 5 years would look like. And I got to the part of that story that was about 2024 because I was kind of curious, right? Like how well did he do? And there's a paragraph in that section where he says like, "Oh yeah, the year is 2024. Um, the best model that is being trained has 5 times 10 to the 25 floating point operations put into it." Uh, and it was kind of freaky that that was so close. And in general, like the lines, the graphs you draw of just computation used in frontier models, like the lines seem pretty straight. Like it seems like this is somehow kind of predictable, a kind of smooth process. Do you know, like, is there something to say about what's driving that smoothness? Like, why is it so regular?
Yeah, this is like a really interesting question, and one that keeps me awake at night. Like, where do these straight lines come from? Right now, my best guess is okay. So maybe let's dive a bit into like what goes into compute, like what makes
Mm.
compute numbers go up. Like, and I will say that there's like two major things that go into that. One of them is that hardware becomes more efficient over time.
Yep.
So then we have machines that can have greater performance. So for like a given budget of money, you can get more compute out of it.
Mm.
It's actually a pretty small number compared to the growth that we're seeing in compute. So like improvements in hardware efficiency at like a fixed level of performance of precision, having improved by around like 35% per year among like GPUs that have been used for machine learning training in the last 10 years or so.
Okay.
But the training compute is like 4x, right? Which is like 5 times greater than this improvement in hardware efficiency. So what
Right.
explains like the rest of the difference? Well, a bit of that is because
And
people have
wait,
been training.
sorry. It's the growth in compute is 4x per year.
Yeah,
The growth in compute efficiency per dollar is 35% per year.
that's right.
Wouldn't that be like 12x as much?
Well, I recommend that you think about this in terms of ohms per year.
Okay.
So, because I think that that helps better like paint the picture. So, 4x per year is roughly like 0.6 orders of magnitude. So, ohm is an order of magnitude.
Yep.
So, 4x is for 4.6 orders of magnitude per year, and 35% is like roughly like 0.12 orders of magnitude per year.
Okay. So it's like four. So it's 4x in terms of the number of orders of magnitude per year.
That's right.
Okay, gotcha. So, sorry,
It's
I cut you off there, but You're like,
Well,
yeah, that
more like 5x.
more
Sorry.
like 5x. But yeah, you were saying that the growth in computation used is just like way faster than the growth in efficiency of like how well we can make GPUs.
That's right,
Okay.
exactly. So what is happening? Like, what is missing? Like, why are these numbers going so high? And I will say that there is like a couple of like less important factors here, like people have been training for longer, which matters to an extent. Also, people have been switching to formats of precision, which like from which they can get more performance, like switching from recently from FP16 to mix FP8 precision.
Sorry, FP16 is just like how many. It's like floating point 16 bits. It's roughly like how many significant digits you use.
Yes, yes,
And so they were using something like 16 significant digits. Now they're using something like 8.
yes, that's right.
Okay.
And but the most important factor overall is just that people are willing to put in like so much more money
Hmm.
into this. And now, of course, like this raises a natural question, which is like, how do they decide how much money to put in, and why is this? Why have they decided to scale the amount of money that's being put in at a rate that results in like this smooth growth?
Hmm.
And here, I don't really have like a very authoritative questions. I have like some guesses. Like one of them is that, for example, there was a recent interview that Demis Hassabis gave, where like he was like, well, like when you're scaling models, like this is a bit of like an art, and you want to be careful that you don't like train a model for very long, but then like the train run like goes horribly wrong. Like you really want to have like this learning curve in which like you progressively learn how to train like larger and larger models
Hmm.
and test out like your different hypotheses about like which techniques are going to work at the scale. So this is like one story of like why people are choosing to scale so smoothly, which is that they believe that they will learn a lot over the process of training smoothly, and not like waste a lot of resources on a training run that might not go anywhere.
Okay.
Yeah. That there's perhaps like another explanation that we could give here, which is that like doing a training run that's very large is like very expensive, right? So again, like GPT-2 in 2019, like it was $100,000 to train, but 5 years later it was like so much cheaper, right? So to an extent, you want to wait. To do your very large training runs, because you're gonna have like much better ideas about how to make the most out of your training run, like better algorithmic innovations that help you make the most out of the compute that you have. And also to a smaller extent, like you're gonna have better hardware, which I've already said is not that big of a deal, but it's still a deal.
Like in some sense, this is a reverse interest rate, right? Like
Yeah,
your money's more useful later than it is now.
exactly.
That's kind of a weird thing to think. This feels like the kind of thing that somebody would have studied, like like what to do when interest rates work that way or something. I don't know. Maybe I'm thinking about it weirdly, but
So actually, one thing that I just thought of, so you were telling me about like this reversed interest rate and like this phenomena where your money is so useful in the future. And one fun observation is that to an extent, this limits how long people are gonna be willing to train models for.
hmm.
Because if your training run just takes like a very long time, then at some point you will have been better off just starting later and
Hmm.
just doing like a shorter training run, but with the more the increases in efficiency that will come associated with doing a training run later. Like there was this like one interesting analog here is that in the 90s there was like this project to sequence the human DNA. I'm
Hmm.
not super familiar with the details, but if I recall correctly, there was like a first project that tried to do this and using like earlier technology, and that went on for like many years. And they were beaten by a project that started later because some years later there was like a better technology that was like so much more efficient that we were
Hmm.
able to like finish sequencing the genome like much faster than the project that had started earlier. So this is a situation that might be analogous in AI, in which like if your plan is just to do like a 10-year training run, then you're gonna be like completely outclassed by people who like start in the last year and just like use like these much better kinds of hardware and much better algorithmic insights to train like a model that's gonna be far better than the 10-year training run.
Sure. So actually, this gets to a question I had about this, which is that like, so it takes some amount of time for models to train, right? And if you're deciding like you have this graph with little dots, right? You know, the dot, the x coordinate of the dot is like when the model was trained, and the y coordinate is how much computation was used. But like, you have to pick a date for when the x coordinate is, and like, as far as I can tell, your like if computation is growing at like 4 to 5x per year, then it seems like it really matters if you put that dot at the start of the training run versus at the end of the training run. If it takes like more than 1 month to train these things, which I think it does, like, how do you make that choice to figure out how to think about like when a model is trained?
Yeah, this is an excellent question. So right now, what we do just pragmatically is the date that we choose is the date where the model becomes public and becomes like officially released.
Okay.
That's what we pick. Just because when you don't some many times you don't know when people really start the training.
Yeah, I wonder if that means that like there could be an apparent like massive boost to these times just by a company deciding to release their results, like announce their models slightly earlier, or like, but like if a company decides to like move the date in which they announce a model forward or backward by 1 month, that's gonna like make a difference to this trend, right?
It will, yeah, absolutely. So you can maybe like the best way of thinking about it is that one is the scale of the models that we have access to, and the other is the scale of the models that are being trained right
Hmm.
now, or that companies are internally testing. And you should expect this the models that are internal to be like potentially like 2x or even 4x larger than the models that exist right now.
if if we're like increasing the amount of computation that's being used to train these models so quickly, like, there's only so many computers that exist in the world, right? At what point are we just going to run out of computers to train stuff on?
This is an excellent question. So, in order to conduct these training runs, the magical thing that you need are GPUs or like hardware accelerators that are like optimized to do these large training runs, which mainly consist of matrix multiplications.
Yep.
And right now, there's essentially like one seller in the world that produces this that sells these GPUs that relies on the services of like one company in the world
Hmm.
that's producing them. This is this very unusual situation in which the supply chain for like these for GPUs is incredibly concentrated, right? So these companies I'm talking about is Nvidia is the one who's designing them, an US based company, and the foundry that's actually producing and packaging the GPUs is TSMC in Taiwan.
So Taiwan Semiconductor Manufacturing
That's right, company.
Company. Okay. So like very small number of companies actually making these, computers.
That's right, and each of them like roughly accounts for like 90% of their respective market in terms of design and in terms of manufacturing.
Hmm.
And this leads to a situation in which like there have been historically some shortages. So for example, like in the last year there was this the release of this new GPU, the H100, that people really wanted to have H100s for training. They're very good for training.
Hmm.
So what they found out is that they quickly ran out of their offer. Like they couldn't meet the demand at least immediately, and they had to massively expand manufacturing capacity in order to meet the growing demand for these H100 GPUs. And this naturally raises the question about like how many how many GPUs can they produce at this moment, and like how much they can expand that in the future. This is something that we're like actively trying to grapple with at the question. Maybe I can give you like a bit more insights into like what's limiting the increasing capacity. And right now, like I will say that the three main factors that are physically limiting increases in capacity of GPU production are first of all packaging equipment. So like once you have the process for producing GPUs is first you create like a wafer which has the necessary semiconductors for it, and then like you need to package that together with like a high bandwidth memory and the other components that make a GPU, and solder everything together into like the actual physical GPU that you plug into your data centers.
Okay.
All right. The technology for doing that is called chip on wafer on substrate technology, or CoWoS technology. And but right now, my understanding is that people are really limited on the amount of machines that can do this CoWoS packaging, and that's why they weren't able to produce as many H100s as they could have sold, essentially.
Okay.
Together with that, you also need the high bandwidth memory units, and this could potentially become a bottleneck. I'm a bit less informed there. And this is what's limiting production right now. But in the future, what might limit it is the production of the wafers that have the semiconductors in
Mm.
the first place, which might be quite tricky to scale up, because in order to produce those wafers, you need advanced lithography machines that right now are also being produced by a single company in the world, which is ASML in Holland.
Okay.
So in the long term, the growth rate of like these wafer production capabilities might determine like the growth rate of GPU production. Now, these are the physical factors. This is like the physical reasons why TSMC is not producing like more GPUs that they could sell to Nvidia, so that Nvidia can sell to its customers.
Mm.
But there might also be some commercial slash social factors at play here. For example, like TSMC could definitely like, my understanding is that it could definitely like raise prices for like their GPUs. Like Nvidia will be willing to pay them like more money and spend more of their margin on TSMC. But if they do that, they're gonna drive away some of their other customers,
Mm.
and they might be scared of like overcommitting to this AI market, where like they are not sure whether this is gonna be like a temporary fad or something that's gonna that's gonna sustain their business in the long term. And this might be a reason why right now they're a bit scared of like dedicating lots of resources to producing the chips that are used for AI training. If they became more bullish on AI, it's plausible that they will invest the necessary resources to like massively expand capacity, which to an extent they're already doing, but even more than that, so that they can keep meeting like this increase in demand for GPUs.
Okay. If I'm thinking about this, so a while ago, I just committed this number to memory, which is roughly 10 to the 31 floating point operations. And the way I came up with that was I said, okay, what's some crappy estimate of like how many floating point operations I can buy for $1, you know, or the per dollar cost of floating point operations on really good GPUs, and then I multiplied that by what's the gross world product in 2019. Just like what's the total amount of goods bought and sold. In some sense, this is kind of a dumb estimate because it might cost them more if they had to like make more machines or whatever, and also like it's sort of weird to like in a world where we spent like 100% of the gross world product on computer chips, that world will look very different. Like, how are people buying food or whatever? But like, that was my weird estimate of just like how much computation should I roughly expect to see until we run out of computers. Do you think like how good an estimate is that? Like, am I off by one order of magnitude or like 10 orders of magnitude?
Let me think about this for a second. Like this is a good question. So right now, to give you an idea, the amount of GPUs that of state of the art GPUs that TSMC is producing is in the order of like 1 million per year
Okay.
for like the H100 series. Okay.
Okay.
Each H100 like has a capacity of like 10 to the 15 flop per second.
Okay.
Okay, and this is for FP16, if I'm not mistaken.
Okay.
How many seconds are there in 100 days? I think that's like 10 to the 7 seconds, if I'm not mistaken.
Um. I'll you. I'll do that math and you can keep going.
Nice, excellent. So we have here like six orders of magnitude GPUs in the 6 order of magnitudes, flop per second in the 15 order of magnitude, and seconds in 7 order of magnitudes, pending confirmation. So like roughly, if you add all of these together, then like you will have 7 plus 6, that's 13, plus 15. This is 28. So like you will end up with like a flop budget per 100 days of like 10 to the 28 flop. Okay, so this is roughly like if people were magically able to like gather all the H100 GPUs that are being produced right now and like put them together in the data center and use them for training, which like will have lots of complications associated with it. To be clear, like they might be able to train a model of up to 10 to the 28 flop, which will be like 3 orders of magnitude greater than GPT-4.
Okay. Yeah, I have roughly 10 to the 7 seconds in 100 days.
Nice.
So 5 times 10 to the 25 is what we currently have, and 10 to the 28 is what we could do if people spent 100 days training. I guess you could spend like a couple 100 days training, but maybe 1,000 days training is like. Should we expect people to at some point just
Train for longer.
3 years of training?
This is actually a fun ongoing conversation within Epoch, which is whether we expect training runs to go for longer or higher. So I already talked about like what's the incentive to do it for lower, which is that you have all these algorithmic improvements are happening, and hardware also gets better over time, which naturally makes it to want you to shorten your training runs. But the reasons why you might want to lengthen it, like one of them is just like raw output, right? Like if you train for like 10 times longer, then you get like 10 times as much compute. And this is like something pretty straightforward. Also, if you train for longer, that means you need less GPUs to reach like a given level of performance,
Right.
and also you need like less power to power those GPUs in the first place.
Why? Just like less joules per second because you have fewer GPUs, and so in any given second you're using fewer joules.
That's right.
Okay.
That's right. Um, there's like this kind of incentives for training for longer, and at this point it's like not obviously clear like which way the balance tips at this moment. And what we have seen historically is that there is not a clear trend in training runs, but there's overall an increase that we have seen from like people training for like 1 month 7 years ago to training for like 3 months right now. Like this is kind of for the training runs where we have information, like training for 100 days seems to be something a typical training run length. I think right now my very weak epistemic status is that I expect training runs to become longer, and I could expect them to become like up to twice as long and maybe up to 3 times as long as they have now. Longer than that, it starts becoming like a harder ask because of these factors I mentioned, and also because just like sustaining a training run for more than a year,
Right.
like that's technically very challenging.
Right. Just there's some rate of like random things going wrong, like something crashes, like there's
That's
a power
right.
outage or something.
That's right.
Gotcha. Okay, just thinking about this number of just how much computation is there available for AI training. So, you're saying like 10 to the 28 flops being floating point operations total. If you want to train for 100 days, on like 1 year of somebody's production of H100 GPUs, right?
That's right.
Do you have a sense of like how that number grows over time? Like in 2030, is that number going to be like 10 to the 29, or is it going to be like 10 to the 35?
So this is something where I don't yet have very well developed intuitions. We're looking into that into this at the moment. My sense is that this could plausibly go up by a factor of 10 somewhat easily. That will correspond to. So if I, oof, I really don't know these numbers off the top of my head.
Fair
Do you
enough.
want me to check them?
Yeah, sure.
Yeah, do that. Okay, so my understanding is that right now TSMC is dedicating around 5% of their advanced node wafer production to making NVIDIA GPUs.
Okay.
I could see. I think it's quite plausible that that might increase by an order of magnitude if they decide to prioritize AI and auth, and if they are able to solve the packaging constraints and high memory bandwidth constraints that I mentioned earlier. So I think it's quite plausible to that they will be able to produce like and to be producing like up to 10 million GPUs, state of the art GPUs per year.
Okay.
which will, if you were to train on that, will allow you to reach scales of like up to like 10 to 29 flop or so. Maybe you increase this a bit because like you might not only use the production from a single year, maybe you stockpile and use the production from previous years as well, and also there might be there will be like a few advances in the performance of the GPUs. Like we will have better GPUs in the future. Like we will already have the B200 in the horizon, and there will be more in the future. I am sure. So I think that all in all, I think it's quite it's quite it would be good. It's good to think that by the end of the year, we will be if you were to dedicate like the whole production of GPUs on a single training run, like you can plausibly reach like up to 10 to the 30 flop. That seems reasonable. You know, it's quite unlikely that you're gonna be able to use the whole stock of like GPUs on a single training run. Like there's first of all, like companies are gonna fight with each other. Like different actors are gonna want to just do their own training run, which means that the resources are gonna be naturally split,
Hmm.
and perhaps like some companies will want to use a large part of their GPU resources for inference. Like for example, like right now, if you just look at Facebook. So Facebook plans to have like bought like 100,000 H100 GPUs just last year, and they plan to have like a fleet equivalent of like 600,000 H100 GPUs by the end of the year, if I'm
Hmm.
not mistaken. But they're not using that many resources on their training runs. They're using like a much smaller, so only a small fraction of those for training, where
Hmm.
most of it is being used presumably for inference right now, and
Right.
this might continue in the future depending on how much value labs assign to developing these new models.
Yeah, I think wasn't there an Epoch post by Ega Erdil saying that like you should expect companies to use about as much computation on inference as training?
That's right. So this is this he had like this neat theoretical argument where like he argued like so there are ways in which you can train a model for longer
Hmm.
and make it without altering its performance, but make it more efficient at inference. Like the most straightforward way of doing this is you train a smaller model but for longer,
Right.
so that in the end it has the same performance, but this is a smaller model, so it's going to be like more efficient to run at inference time.
Right.
And if you think about this and you put yourself from the perspective of a company that wants to reduce the total compute that you use between training and inference, then naturally what you want to do is like try to make these two equal, because that's what they're going to minimize like the total expenditure of compute that you're going to be making. There's some caveats here, like inference is usually less efficient than training. Like the economics for inference and training like are not exactly the same. And right now, my understanding is that this is not happening. Well, I think this is not happening in companies like Meta. I think that this might be quite well plausibly happening in companies like OpenAI, in which like they use like very large amount of resources for training. Like it is quite plausible that given what we know about how much inference is going on at OpenAI, that their yearly budget for inference is similar to their yearly budget for training. But yeah, at this point, this is something that I think is informative, and I think it has like this neat, compelling force as an argument, but it's
Sure.
also something that I want to get more evidence on whether this is actually going on before relying on it a lot.
Fair enough. So way earlier when I was asking you how AI was going, the second thing you mentioned was algorithmic improvements. So I think the a thing that um, a post people can read about this is algorithmic progress in language models by Anson Ho et al. Well, it's a blog post and it's also a paper if you've got time for that. So basically, this was saying that there's um, or the way I parsed it was that there's like something like a 2x speed up in training models to the same loss every 8 months or so. Like maybe the error bar was 5 months to 14 months. So my understanding is the way this worked is that you picked some like degree of loss that you wanted to get to, so some like level of performance, and then you tracked like how much computation would it take you over the years to reach this level of performance, and that's where you get this number from.
Yes and no.
Okay.
So this is kind of the abstraction that we're going for, and we're hoping that this will be one of the applications and interpretations of the model that we built.
Okay.
But in the end, what we did is actually like the data that you have is very sparse. Like there's very few people who are doing like exactly that kind of experiment, exactly the level of performance that you care about. So what we did is a bit more general in that we just look at like lots of models that had been already trained. This is like an observational study, and we looked at like which performance did they achieve in terms of perplexity of like the loss that they achieved on the texts, how well they were able to simulate the text they were tested on,
Hmm.
how what was their scale in terms of model size and data, and then also in which year they were trained. And essentially, we just fit like this regression, which is like, well, I'm giving you like the model size, I'm giving you the amount of data, and I'm giving you the year that it was trained on.
Hmm.
And it's like, what would you predict? That this model tries to predict like what is the performance that the model achieves, and we
Okay.
fit like 14 different ways of 14 different equations that try to combine these terms in different ways, and finally choose one of them that intuitively seems to resonate with how we think that a scale and performance relates to each other, and also the role that we think algorithmic improvements plays into this.
Part of what I'm wondering here is like how sensitive are is this number just to the specification of how exactly you define the question you're asking? Like conceptually, if I picked a different loss level, would that change it from like every 8 months to every 3 months or to every like 2 years?
Yeah, so I'm going to introduce you to the bane of my existence,
Hmm.
which is scale dependence.
Yeah.
So through this model, like one big assumption that we introduce is that these algorithmic improvements they work independently of the scale that the models are trained on. So
Yeah.
like we here we make like this arguably unrealistic assumption, which is that if you come up with like a new architecture, then like new architecture is going to help you get like a fixed level of improvement, no matter if no matter if you are just training at like a larger scale or like a smaller scale.
Hmm.
Now, this is arguably how not how things work. Like it could be quite plausible that, for example, like we think that the transformer scales much better than recurrent architectures right now.
Hmm.
But this might be only up to only if you have like enough scale for like the transformer to kind of like kick in and like start at these like great properties of a scaling. Like if you're working below that scale, you might be better off with like a simple with like a simpler kind of architecture. Like this is not something implausible to me.
Okay.
What this means is that our estimates might not be sufficiently accounting for like this difference in like how you should expect improvements to be better at the frontier of compute, or whether you should expect them to be better at the for like a small scale budgets. And this matters because there are two reasons why you care about algorithmic improvements. Like one of them is that they help frontier runs to be like much more efficient and reach like new capabilities.
Hmm.
The other one that you care about this is because this helps like a wider amount of people train models with like a certain level of capabilities, right?
Right.
So depending on which these two use cases you care about, you're gonna care more about like innovations that work better at the scale, or innovations that work better at the small scale and small compute budgets.
Fair enough.
This is something where I will want to have like a better, more scientific understanding of to which extent this is the case, and try to look at the specific techniques that drive this algorithmic improvement, and try to see like at which scale were they first discovered, and in which scales do they apply, and does the efficiency of the technique like change depending on at which scale it is applied. Like I wouldn't be surprised to find that, but right now we don't yet have like a systematic study showing this.
One thing that I'm kind of confused about when I'm thinking of algorithmic improvements is people authoritatively tell me that there's these things called scaling laws for language models, and these scaling laws say like, look, it's this formula, and you put in how many parameters your model has, and you put in how many tokens you're training your language model on, and it outputs, what loss you expect to reach on your data set. I thought that if I knew the number of tokens you were training on, and I knew the number of parameters your model had, and if I assumed that you were looking at each token just one single time, so only training for one epoch, which I gather is what people seem to be doing, I thought I could figure out how much computation you were using to reach a given loss. So, are algorithmic improvements are those things that are changing these scaling laws, or are those like ways of better using computation within the confines of those scaling laws, or something else?
So scaling laws are defined with respect to a specific training method and with respect to a specific architecture. So, for example, in the famous chinchilla scaling laws paper by Hoffman et al. From DeepMind, they study like this particular setup in which like they have a transformer and they define like very precisely like, okay, how are we gonna scale this? How are we gonna be making this bigger? There's lots of prescriptions that go into this. Like for example, when you scale a model, you have lots of degrees of freedom on like whether you add more layers or whether you make the model wider to have more neurons per layer.
Right.
So these are all like other considerations that affect like the end result, like the scaling laws that you're going to fit. And kind of like you can think of these algorithmic improvements as going beyond the specifications of like the particular confines in which the scaling law was originally studied, and try to introduce like, well, different tricks, like new attention mechanisms in the architecture, or like maybe you're training on like a different kind of data that has higher quality and allows you to train more efficiently. Maybe you change the shape of the model in like a different way. These are all the ways that you can escape the confines of the scaling laws.
So is this basically just saying that scaling laws, like I kind of thought of scaling laws as somehow these like facts of nature or whatever, but it sounds like you're saying they're just like significantly more contingent than I'm thinking. Is that right?
I think that this is right in an important sense, and maybe there's like a wider sense in which maybe they're a bit more general. So in the specific sense, is like in the experiments in this scaling laws, like we see that it's like the scaling laws is study like a particular setup, right?
Hmm.
And we can make some assumptions about how much this is going to generalize, but it's kind of tricky, and there's right now like dozens of scaling laws paper that study different setups and arrive at like slightly different conclusions.
Again, to kind of stick in this scaling laws frame. So you've written down a sample of scaling laws on your piece of paper. So total loss is some like irreducible loss, which we're going to call E, plus some constant divided by number of tokens to some power,
Mhm.
plus some constant divided by number of parameters to some power.
That's right.
And basically, like the things that determine a scaling law are what you think the irreducible losses are, and then for parameters and data set size, what you think the like exponents of those are, and also what the like constant factors out the front are.
That's right.
If I'm thinking about algorithmic improvements, are those mostly changing the exponents or are they changing the constant factors? Like it seems like this is going to matter a lot, right?
It does matter a lot, and this goes back to scale efficiency. So if you were changing the exponents, then
Hmm.
like the efficiency of the improvements will change with the scale. But the way that we model it in the paper is essentially as a multiplier to the effective model size and the effective dataset size
Okay.
that you have.
I guess that's not quite changing any of the constants, but it's like, yeah, somehow you're using something instead of n, and okay. I guess that kind of suggests that maybe you could create a meta scaling law where like you have the scaling law with these constants and the constants are like varying over time or something. Is this meta scaling law? Is it like easy to write down? I feel like someone could get that on a T-shirt.
Yes, I mean that we have 14 different candidates for that in our
Okay,
in our
all
paper.
right. So I guess people should take a look. Part of the reason it seems like someone would want to ask this question is basically trying to ask, okay, if I'm thinking about AI getting better, is that mostly because of increasing computation, or is that mostly because of algorithmic progress, or is that mostly because of increasing the amount of data we're putting into models? I think you frame it like this to some degree in the blog post.
That's right.
One way that this could be kind of misleading would be if algorithmic progress were driven to some degree by increasing availability of computation, right? For instance, maybe if you have way more computers, you can run way more experiments and you can figure out just better algorithms to run. do you know to what degree this is what's driving it?
Yeah, you're right on the money here. Like this is something that will be quite crucial for like how AI will play in the future.
Hmm.
The extent to which this algorithmic innovation is itself being driven by compute. And to be honest, like I don't have here like a great answer at the moment. Like my personal belief is that it actually plays like a large factor, and this is being informed by some informal conversations that I've had with people in different labs and rumors that I've heard where like people say like, oh, we're very limited by compute, like we don't hire like more researchers because a researcher will just take up like precious compute resources that our researchers are already using for like trying to come up with like better ways of training the models.
Hmm.
So it seems that to a degree, at least in some labs, people have this notion of like our research is compute bound. Our research is also being greatly determined by the access that we have to computing resources. And this sounds like quite reasonable to me. Like the main way that we learn things in science is you run an experiment, you see if it works, and then you try it again in like slightly different variations. And particularly, like it seems that a scale like is testing whether a problem scales, testing whether a technique scales is very important for making like these advances. So that naturally like limits a lot like the amount of advances that you can do if you are constrained by a compute budget. And this might have like this huge relevance on like how the future plays out, because imagine that we're in a world in which like you're bottlenecked by ideas, you're bottlenecked by having more researchers that can do that. Like
Hmm.
plausibly in the future we're gonna have AI that's gonna be like really good at coming up with ideas and like substituting for like human scientists and like coming up with this hypothesis of what you should train. And if you are bottlenecked by ideas, like this could like quickly lead to like very massive improvements in algorithmic efficiency. But instead you're being bottlenecked by compute, then it's like, well, sure, you have like all of these virtual researchers that are going to be working for you and like coming up with great ideas, but they're still going to have to go through like this bottleneck of like we need to test their ideas and see which ones work. And they might be more efficient at coming up with ideas, and still like this could lead to like a substantial increase in algorithmic progress over time. But this might be like much more moderate than in the other world.
So I guess this gets to the question of what the advent of really superhuman AI is going to look like. And yeah, I think classically people have thought of we're just going to have like tons of AI researchers. Um, I mean, if the bottleneck is compute, like compute doesn't just we don't like just get it from rocks, right? Like some people are like building machines and figuring out how to like do things more efficiently. Does that suggest that the singularity is going to be like entirely contained within like the Taiwan Semiconductor Manufacturing Company?
Um, Fun question. I mean, right now, like the two parts that go into AI progress is you have the hardware manufacturing, but then you also have like the software companies that are like a completely separate entity that are like coming up with these ways of training them. So like by default, I guess that we will expect like something like that. But there will be like this really vested interest on like on the both the semi-factoring company but also the AI companies to apply AI to increase their own productivity. I think particularly like this is very naturally happens within AI labs, especially because AI is very good at coding. AI is very good at like the things that are useful for doing AI research. I think it's very natural that people will want to see, can we use this to improve the productivity of like our very expensive employees.
Hmm.
On hardware manufacturing, it also feels like this natural like multiplier where like if you are able to use AI to like increase the productivity of TSMC,
Hmm.
then sure they're gonna be able to like produce much more. This is gonna lower the prices of compute. This is gonna allow you to train like even larger and better models that help you achieve better levels of like generality and capability. So to an extent, I think that the intuitions that I have is that I do expect that some of the early use cases for like very dramatic increases in productivity are gonna be in A companies,
Hmm.
and I will not be surprised if semi-factoring companies, semiconductor manufacturing companies are
Sure.
next in line.
Okay. And I guess that suggests so a lot of just work being done both in AI in general and a lot of what you're checking is scaling laws for like language modeling for these predictive tasks. I wonder if that suggests that like actually we should be thinking much more about AI progress in whatever a good analog of making computer chips is. Like I don't even know what a good benchmark for that is in the AI space. I don't know. Do you have thoughts about that?
So I think what you were pointing at is like, oh, maybe one type of task that we really care about is to which degree AI is going to be helpful for like improving chip design, for improving like for participating in the processes that go on within a semiconductor manufacturing company. Is that what you were pointing at?
Yeah,
Yeah, I think that I think that this is right to an extent. It's tricky to design good benchmarks that really capture what you care about. Like the benchmark you really care about is like, does it actually improve the productivity, which is something you will see in the future once you get the models deployed there. But it will be interesting to start developing like some toy settings, which try to get at the core of like, oh, what will it mean to increase the capacity of this model? So, like for example, one of my colleagues at Epoch, JS, like he has been thinking about like, oh, what kind of benchmarks could be cool to have and could be informative about what we're thinking about in AI. And one of the things he was considering, this is more on the software side, but he was considering like, oh, can we predict like, can we have a benchmark that's about predicting the results of like an AI experiment? And this is again, this is more on the a company side, but this will act as this could act as like a compute multiplier, right? Because
mm,
if you have like 10 ideas, but if you have only compute to test 10 ideas, then you want to be picky with like which ideas you test, and it's better if you have like these powerful intuitions about which ideas might work. So to the extent that AI can help you provide with these intuitions and guide your search on which techniques to try, like it's going to allow you to it's going to allow you to effectively like test increase the range of options that you're considering, quickly discard ideas that you think are not going to work, and really focus on the ones that are worth testing and trying at the scale.
sure. So, okay, we've talked a bit about algorithms. We've talked a bit about computation. I think a lot of people think of AI as basically this three-factor model. There's like algorithms, there's computation, there's data. You pour those three into a big, data center, and out plops GPT-5, right? Um, is this basically a good model, or is there something important that we're missing here?
So I think that this is a good model, though I will make like this distinction, which is that you really care about which constraints are taught at a given moment. And at
Hmm,
this moment, like I will say that compute is a taught constraint, whereas data is not.
okay,
So right now, models that we have are being trained on like for the ones where we know the data set size, like they use around like 50 trillion tokens of data.
okay.
And the size of common crawl, for example, is like 100 trillion tokens of data roughly. And
And
if you
common crawl is just roughly the internet, or is it like half the internet?
it's like a fifth of the internet. So if
Okay,
you look at indexed, the amount of content in indexed public text data, that would be like 500 trillion tokens of data.
okay. So common crawl is 100 trillion tokens, and people should think of a token as being like 80% of a word on average. Yeah, roughly 100 trillion words of data that you can get from common crawl.
That's right.
And so you're saying that data is not the taught constraint right now.
It is not, quote unquote, maybe there's some uncertainty here. Maybe in the future AI companies won't be able to use publicly indexed data anymore to train their models. There's some complications here, and also there's some domains for which like you really want to have like data there. Like if you really care about accelerating experiments, you
Hmm,
probably want to have data about coding. You want to have high quality data about reasoning on AI, and you might really want to expand those kind of data. But yeah, the first order approximation, like the reason why I think we're not seeing larger scale training is because there aren't enough GPUs. Like if people had more GPUs, they will find out ways of gathering the necessary data. So in that sense, I think that compute and algorithms are like more important to track at the current margin that data is.
okay. Well, even though it's less important than the other things, I do want to talk about it because you had this interesting paper. I mostly just read the blog post. Will we run out of data? Limits of large language model scaling based on human generated data. This is by Pablo Villalobos and colleagues. Um, so my understanding of just the top line results is that there's roughly on the public internet, there's 3 times 10 to the 14 tokens that you can train on, which is like 300 trillion, if I can do math, which is unclear. So roughly that many tokens to train on. And you would have a model with roughly like 5 times 10 to the 28 floating point operations that you use to train on that. And roughly in 2028, we'll just be using all of the training data. Is that like roughly a correct summary, or is there like something important that I'm missing?
That I think that that sounds about right. So it's interesting to compare this with the size of the. We were talking before about like, oh, if you were using like all the H100s that are produced in a year, like what's the largest model that we can train, and we
Yeah,
arrived at like 10 to the 28
right.
flop or so, right? If you were using like this 100 trillion tokens of data in order to train it, like in order to estimate like what's the largest model that you could train, like maybe one approximation that you can do here is think about the chinchilla scaling laws that can inform you about like with this amount of data, like what's the largest model you can train. Like roughly you will be using like you want to use like 20 tokens per parameter of the model,
Okay.
um, for training it according to chinchilla optimal scaling. Lots of quotes and quotes here.
Okay.
So that will mean that if you're using like, let's say you use like these 400 trillion tokens of data that are all in the indexed web, and
Okay.
that will allow you to train like a model that has math
20 trillion.
20 trillion parameters. So then that will lead you to an amount of compute. So the amount of compute is roughly 6 times the amount of data times the amount of parameters. So that's gonna be uh, this is 4e14 2e14. So that's
Nope. 2E13. Because it's 400 trillion, but only 20 trillion.
oh yeah, that's right. You are right. And here I multiply by 6. This is going to be 8 times 6. That's 8 times 6 is
It's 12 by 4, which is 48.
yeah, so 50 essentially. So it's 5 a 28. Yeah, which is what we arrived at before, right?
Yep, 5 by 10 to the 28. Oh man, it's nice to see that in action. I was actually wondering where that number came from. Okay, cool.
Nice. So what you see is that now there is enough data on the index web to train like to train something that would be 5 times greater than what you will be able to train with like all the GPUs in the world.
Yeah. So this is kind of interesting to me because there are a few coincidences here, right? Like, yeah, one is the thing that you're just noting that amount of data you can use. Like, if you had 5 years of global GPU production, you'll be able to train on all of it, chinchilla optimally. Another thing I noticed is I looked back on the training compute growth paper and I looked at, okay, what's the biggest model right now, and when do we hit 5 times 10 to the 28 floating point operations? And roughly, uh, I don't know, depending on like whether it's like 4x or 5x, and depending on whether I can multiply, it's somewhere between 2028 and 2030. So like somehow there's this kind of strange coincidence where like if you extrapolate compute growth, you get enough compute to train on the whole internet. Also, just at the time when we are projected to train on the whole internet, is that is that a coincidence, or is that just a necessary consequence of frontier models being trained roughly optimally?
No, I think this is a coincidence. Like what has been driving the amount of data on the internet is just like adoption of the internet and user penetration rates, which have nothing to
Right.
do with AI and GPUs. So I think this is just like this
Yeah.
happy coincidence.
Well, the 2028 number was when it was extrapolating how much data models were being trained on, right? So that does have to do with AI.
Sorry, so like these the number that we derive now, like this 5 times 10 to the 28,
Yep.
like this is based on like the amount of data on the index web, which has nothing to do with AI, right?
Right, right, right.
Like what has to do is like when you do this extrapolation is like when do you hit that amount of compute. But like that because this is similar to like what is a what is a coincidence.
Hmm.
is that the amount of the training run that you can do on this amount of data is so similar to the amount of the training run that you can do on the amount of compute for the GPUs.
Gotcha. So now I want to ask a bit about the future of AI. So a while ago, you wrote this. You guys put out this post called "The Direct Approach," which was roughly saying, okay, here's a way of turning loss into like how much text an AI can write before you can like distinguish it from a human. And roughly, it was a way of saying, okay, if you want an AI that is smart enough to write a tweet just like a human could, that happens at like this amount of computation. If you want to get an AI that can write a scientific manuscript about as well as a human can, that happens at this amount of computation, modulo some fudge factor, which is like very interesting to talk about. But if I looked at those numbers, it said like maybe I needed somewhere between like 1 times 10 to the 30 and 3 times 10 to the 35 floating point operations to get AGI that could write, be roughly as smart as people. Um, but when I'm training on all the publicly available data on the internet, I only got that was only enough to use with 5 times 10 to the 28 floating point operations. Does that mean that scaling just isn't going to work as a way of getting AGI?
So I will say two things here. The first one is that I will mostly think about this method about as trying to estimate like this upper bound, because presumably like you don't need to be able to mimic humans perfectly in order to write scientific manuscripts of perfect quality, right? Like this is
Hmm,
like this kind of this unrealistic goal in which like your model's like so good at mimicry that you cannot tell it apart. But it doesn't have to get to be that good in order to like be have like a transformative effect on the economy or produce manuscripts of quality. Like it's much harder to write to write something that like mimicking someone than
right.
to write something useful, right?
Fair enough. Fair enough.
The part that the other thing that I will say is that like I will caution people to take these numbers like very seriously. Like I think that right now we just don't have like a really good understanding of like when do you hit like the when do you hit different levels of capabilities and at which scales. Like I think we have like this rough notion about, yes, once you increase in the scale you get like more and more you get more and more capabilities and more generality, and if you combine that with like certain scaffolding techniques, like this might lead to like AI that's like widely very useful. But when it comes down to saying like, well, this is going to happen at like this amount of flop exactly, like it's a very rough job. There's like maybe some suggestive numbers that I will float around. Like one of them is this that comes out of this paper, like trying to estimate like, okay, in this kind of like setting, like how much compute you will need to train a model, if like a scaling laws can be sustained for like 10 more orders of magnitude, which is also another big if. What other numbers are like suggestive to think about? So one thing that's quite interesting is, so I forget exactly who it was right now. It might have been Coursewell, who like 20 years ago,
Hmm,
like they made some predictions about when will we have AI that's essentially that will like pass the Turing test. And they said something like, well, we forecast that the point where you will have like enough compute to match the human brain will happen like somewhere in the 20s, and that happened,
hmm.
which is insane. Right? Like they got that right. Like it's actually true that we have now models that essentially pass the Turing test and that they can converse with like with humans and have like a meaningful conversation with them. So it's quite insane that just by looking at this biological construct of like the amount of computation going in the brain, and with like some wild back of the envelope calculations, they were able to do that. How can we go about like is there like an analogous thing that we can do to talk about like when we will have AI that's like really good and can do essentially everything that humans can do? So there was this report by Aya Kotra where like she looked at like a few of these like biologically inspired quantities, and I think that one that has like a some hold in my thinking on the upper end is like the amount of computation that was used to essentially run evolution and give birth to human species, which like she estimates to be like around like 10 to the 40 flop, what you will need to rerun evolution. There's lots of caveats going into that. Also, like if you account for like, oh, we might have gotten lucky with like this run, but maybe it could have taken like much longer. Like maybe a more conservative estimate could be like even up to the 10 to the 42 or even 43 flop, what you will need to recreate human evolution or so. And that feels to me kind of like this. Okay, that's the frontier. That's like a like if we had that amount of compute, then it's no longer about compute.
Mm.
It's more about like, are we do we have like the necessary techniques to use it productively to create intelligence de novo. And so this is now like something that has like this kind of hold in my thinking about like, well, I don't have like a very great idea about like at which level of compute we will see like AI that can participate as like a fellow worker in the economy. But it's probably not 10 to 26, because we are pretty much already there. Like I don't think that this is right in the horizon. It's probably not 10 to the 40 flop. Like that seems like this is too much. Like if you had that much amount of compute,
Mm.
like you will be able to again like rerun evolution. You probably can do better than evolution at like creating intelligence with current techniques. I will think so. I think it's not crazy to argue that. So then it's like, well, it's somewhere in between that. And
Okay.
like where exactly at which order of magnitude, I don't know. Like maybe my distribution looks like pretty uniform between 10 to the 26 and like 10 to the 36 or so.
If I'm uniform, say instead of that, I'm uniform just between 10 to the 26 and 10 to the 40 floating point operations to get, AI that's smart enough to, just do all the science and technology instead of us. Most of that is higher than, the 5 times 10 to the 28 that we're going to use to train on all the publicly available data on the internet.
That's right.
Does that suggest that scaling language models is not going to be the thing that gets us AGI?
So I think that people will become creative once data becomes a thought constraint. So again, like data right now, I don't think is the thought constraint. I think is compute. Like the data sets that people train these models on, at least when training was happening publicly, like it was like a process that it was trained on things like, again, like common crawl or the pile, which are like data sets that were put together by like software engineers on essentially their free time. Like
Mm.
they were not like these very large like industry funded projects to get the data sets. To an extent, like I think that the paradigm is changing, and now like OpenAI is investing a lot of resources in getting data, especially for fine tuning and fine tuning purposes. But overall, for the pre-training, it seems that companies have been able to get away with like just use the data that already exists and is easily available. Once it becomes the case, once this ceases to become the case, like there is this huge incentive to come up with like ways to increase the efficiency of the data, get ways to improve how yeah, get ways to get more data out of like other places. And it's interesting to think about like what these places might be. So like one thing that we're seeing now is people are training models that increasingly deal with more modalities, right?
Hmm.
So GPT-4o, for example, right now is quite proficient at like parsing images and can also produce images together with DALI. I'm not sure if you use DALI of its native image generation. Well, anyway, models right now are increasingly more multimodal, and you could use data from other modalities to try to push back this deadline of like how much data you have available for training. Now, I don't think that this will actually lead to like, if you just look at like image and video data, like I don't think that this will be like a huge delay. Like maybe this buys you like a couple more years of like scaling. Maybe this buys you like an order of magnitude of compute. Um, essentially, I think that this increases the amount of data you have by a factor of 3,
Hmm.
and the amount of training that you can do increases quadratically with the amount of data you have. So maybe this
Okay.
buys you an order of magnitude of scaling
Okay.
roughly. Um, so what do you do if like you have already trained on like all text data on images and video? Like what else do you turn to? And like one thing that's interesting to think about is the model outputs themselves and synthetic data. So right
Right.
now, OpenAI, if I recall correctly, is producing in the order of 100 billion tokens per day,
Okay.
which roughly extrapolates to like 40 trillion tokens per year.
Okay.
So 40 trillion tokens, like, that's substantial. That's pretty high. Like if you were doing that, if you were to keep that up for 10 years, then you will have produced like amount of data that's as large as the size of the index web today. And
Hmm.
if that data turns out to be useful for training, then you might be able to use this in order to continue scaling. And there it's not completely clear at this moment whether that's going to be useful. So there have been like some studies where like if you train models on like regurgitated model outputs, then like they tend to there's this phenomena called model collapse, in which like the quality of the model ends up degrading, right? And we don't have like a really good understanding of that
Yep.
just yet. But again, like this is this is in a sense like the early days of dealing with this problem, because it hasn't been that big of an issue yet. Once it becomes, I expect the forces that be to push really hard to figure out like how do we go past this.
So okay, here's how I'm thinking about this.
Mhm.
It seems like, so if it's really the case that we're running out of data in 2028, or running out of data to train on, and it doesn't look like we're having kind of AI that can really, like, just take over science and technology creation from us at that scale. Like there's this question people ask, which is how many big ideas do we need to have before we get superhuman AI? And if it's the case that, like, we're going to run out of just data to train on before we get there, it seems like that puts a lower bound, saying like we need at least one big idea until we get to super smart AI. I'm wondering if this seems right to you, or like even a useful way of thinking about things.
To some extent, I think like I'm not sure how big of an idea it's gonna be, because the
Okay.
idea might be just like use synthetic data and it works, and it's like, well, good idea, it worked.
So yeah, I guess I want to talk a little bit more about what you can say just about AGI, AI that can take over just scientific and technological progress from humans. So I guess we don't know exactly what level of loss it's going to be at, but is there something to say about, is it like 5 years away, or is it 50 years away? And yeah, let's start with that question of timelines.
Yeah, so maybe the naive way that you can think about this is like, well, we were saying before, like, well, it's probably not gonna be like 10 to the 26 flop. That seems too little. It's probably not gonna be like 10 to the 40 flop. That seems too much.
Hmm.
It's gonna be like, well, it's gonna be like somewhere in there. You get like the required level of compute to make AI that can substitute for humans in scientific endeavors a reality. And then you just think like, well, like how fast are we going, and like how much do we expect compute to go. And like right now, like my picture of like naively what I will expect compute to go like is like, well, it goes like this very very fast for like a few years, perhaps until the end of the decade, perhaps like a little bit more than that. And then like, well, eventually it has to slow down, and like how much it slows down, it depends on like very complicated factors, like on whether, like, for example, we have already found like this successful application of AI that allow you to like increase the growth rate of the economy, or whether like the field kind of like stagnates, like still growing, but you are now bounded by like how fast the economy grows overall, which right now is growing like 3% per year, which is like nothing compared to 4x
Hmm.
per year. Holding all of these things in mind, like, okay, maybe we go like 4x until the end of the decade, and then like by the end of the decade we're training something that's like 10 to the 29 flop or so.
Hmm.
And then like if you keep going, like I don't know, maybe like something reasonable to expect is that somewhere between 2030 and 2050, you might cross like 10 orders of magnitude of compute more or something. Like it starts becoming like quickly very complicated. Like I think that once you are like past to the 10 to the 36 flop per year, you start getting into territory where like you might just melt the earth in the process.
just because of the heat produced by like doing the training.
That's right.
Yeah, I wonder at this stage, like, it seems like right now, computation available seems to be like a pretty good proxy for AI capability because we can sort of hold fixed like there's just this pool of high quality human data that we're drawing from. But like if you're right that we're running out of this data in 2028, it seems like maybe at that point computation is just no longer going to be such a good proxy, and maybe we're just going to have to think way more carefully about like algorithmic improvements or how you can make use of various data like do you think that's right, and do you think that that reduces the value of just these like compute forecasting estimate style things?
TBD. I think that actually, again, like right now, my guess would be that data is not gonna be the most determinant bottleneck, and this is somewhat driven by this belief that people will make it work. Like
Okay.
people will figure out like how we can use, for example, like synthetic data here. Like I don't know, like one example that we have is recently there was this alpha geometry paper in which like they used synthetic data to train like an AI system that was able to solve like Olympic geometry problems, right?
Hmm.
So and generally in especially in scenarios in which like there exists the right answer, like math or programming. Like it seems that one naive strategy you can do to generate more data is like okay, use like the latest generation of models to try to generate solutions to problems,
Right.
and you train on the problems that are right.
I guess so. I next want to talk just a bit about Epoch AI as an
Yes,
organization.
absolutely.
So, why does Epoch AI exist?
So it exists. It was born out of my frustration.
Okay.
So again, like while I was doing my PhD on artificial intelligence, I was like somewhat surprised that no one had yet done like a very systematic analysis of like the different trends that matter for AI. Like there was this post on AI and compute from OpenAI in 2018,
Hmm.
but very little beyond that, which seemed wild to me, given like the huge amount of interest that AI was creating, at least around me, and how important they think that the technology was gonna be for the future. So we started like this whole process of like let's systematically track like the things that go into developing AI models and study the trends and try to get a better picture, a better evidence-based quantitative picture of what the future looks like, and that's how Epoch was born essentially.
So, when I think of Epoch, I think of it as sort of a mix of AI impacts and our world in data. Do you think this is like a fair understanding of what you guys are?
um to some extent, yes. The this might be underselling also like the amount of in-depth research specifically on AI that we do. So like I think a lot of I think a lot of our world in data is like they are like these curators of data that
Hmm.
do not produce like a lot of original research themselves, but instead like are compiling like the collective knowledge of humanity, and this
Fair
is very
enough.
good and very useful. At Epoch, instead, like we're creating the data selves, creating the data sets ourselves, and like trying to generate like this original body of work that people are going to be able to use to inform decisions about AI. Regarding AI impacts, like it's also there are also like close analogs to what we're doing in terms of like trying to think quantitatively about AI. I think that in AI impacts, maybe they rely more on surveys and they rely more on analogies with other technologies in order to inform what AI is doing. In Epoch, we're being a bit more directed and being like, well, this is about AI, and AI is what we are going to be focusing on, trying to understand, keep up to date with what's happening in the AI world and the latest knowledge that has been produced and all of these concepts like scaling laws and such. And then like kind of like the hope here is like I see Epoch's AI work as having like these three work streams. Like one of them is like we collect this data.
Yep.
The second one is like we analyze it. And the third one is like we put all our research together to paint like these quantitative pictures of the future of AI.
So, there's this work that you guys put in to just have this quantitative picture of the future of AI. Like, one way someone could think about this is like, look, the point of information, the point of like knowing things is that it can change some decisions that someone can make. And the more important the decision that, you changed, the more important it was to know the thing. What, like concretely, do you know like what decisions people might be making differently based on what Epoch AI puts out.
This is an excellent question, which gets at who are audiences and like who is changing their mind due to our work. And I think a really important lever here has been policy making, actually. So in the last 2 years, we have seen this surge in interest from governments around the world in governing these new AI technologies, right?
Hmm.
And in order to decide how to govern it, they want to have like this uh, in-depth understanding of like which levers drive development and how they can regulate them. So compute is here like this very clear example, right? In which it's this lever that turns out to be very important for a development. It's also quantifiable. It's something that you can exclude people from, and so it's like this very natural lever for governing. So the way that I think epoch data is being used around the world is in order to inform like these conversations on like, okay, like if we want to create compute based regulation, like how do you decide like at which compute levels you're gonna impose like certain requirements, right? Like for example, the executive order on AI from the US imposes certain additional requirements on models that were trained on over like 10 to the 26 flop. And like I don't know exactly how they chose the number, but like a big suspicion that I have is that they looked at our data and they were like, 10 to the 26 is like something that no model has been trained on yet.
Hmm.
But it's like close enough that in a year, plausibly companies will be trying to train models this big. And this is like a way in which like I could see Epoch's data being useful in order to make this important policy decisions. More generally, like I'm hoping that right now there's many people who are like trying to thoughtfully plan for AI and the advent of these new technologies. And I will want them to be better informed. I will want them to like this make decisions that are based on facts rather than like vibes on what is happening right now in the field. Like this
Hmm.
seems really important, given that this technology might be like the next industrial revolution that we live through.
Sure. So if that's kind of what Epoch AI is for, I don't know. You've got a bunch of work, but there are some, you know, not every possible question has been answered yet. So I'm wondering, like, what are the big open questions that you like most want to address that like don't have answers yet?
Okay, so big open questions at Epoch. Like one key thing that we are constantly thinking about is like when are we gonna reach like different levels of automation and like how fast is it gonna be the transition from a world with little automation to a world with a lot? That seems to be like a very relevant input into many decisions going today about like, oh, should we try to plan for like this period of like very fast automation, like trying to prepare for that? Should this be like is this something that's going to happen in the next year? Is this something that's going to happen in the next 10 years? Like whether different policies and plans for this technology like are actually feasible depends a lot about like when this rapid period of automation begins and like how long the period itself it's going to be. So this is
Hmm.
something that we think about quite a bit. A second important part here is keeping track of like what's driving innovation. Like we want to have like this in-depth understanding of like these factors. We talked about before about like whether algorithmic innovation has this important component that's driven by compute,
Hmm.
and we talked about like, oh, why this will be relevant for painting a picture on the future of AI. So we think a lot about those kind of things, and also more generally about like the different bottlenecks that AI might face in the future. We talked about data already. Other things that we're talking about is so, for example, one sunny thing I've been thinking about lately is latency. Like the in order to train a model, you need to do like a certain amount of serial operations, and this to an extent limits like the largest training run that you can do. We've also started thinking recently more seriously about power and about how much energy you will need in order to train these large machine learning models. More generally, like we want to be able to examine critically like all of these reasons why the current path, the current trajectory of AI might slow down, and trying to incorporate that in our thinking about like when we will reach like different levels of automation. And finally, like we want to think about like how this will impact society. So there is like economists have been thinking long about the effects of automation, but I'm like somewhat even disappointed that so far there has been very little uptake among mainstream economists in trying to think about the consequences of AI and of having like a way of turning computers into workers, essentially.
Mm.
Like I think that there is lots of things that that classical models of economy, like simultaneous growth theory, has to tell us have to tell us about what effects AI might have on the world, and very little work in like just straightforwardly trying to apply like these already well developed, well understood models to the case of AI. So this is something that I will be hoping to see more of in the future. We do have a fair bit of this within Epoch, but I would love for like mainstream economists to also like join the boat and like try to drive the knowledge forward with us.
Yeah, it's weird. Yeah, I also find it weird how little there is in mainstream economics on this. And also, I don't know, I don't think I want, I'm not sure I want to name names, especially because I haven't read the relevant piece, but I think there are prominent instances of this that just do not seem very high quality to me. Um, but so actually related to this, so I read your guys' 2023 like annual update or something, and one thing you said was that you would have this report on AI and economic growth at some point during 2024, and I'm pretty excited for that. When should I expect to be able to read that?
Absolutely. So we already put out a report on economic growth last year, where we talked about like why AI might lead to explosive growth. Like what would be the econ literate arguments for like why you might see explosive growth from AI, and also like why are what are like the most plausible objections that we find to it.
Sure.
But the next level for us, that was more of like this theoretical exercise of walking through like these models of like the economy and like these high level considerations for that. But the level next level for us is like trying to build this comprehensive integrated assessment model of the future of AI that tries to tie together what we know about compute, what we know about the scaling laws, with like these models of like the economy and scientific progress.
Mm,
And the hope here is that in the end we will have a tool that is really helpful for like describing real, if not realistic, like at least illustrative pictures of what the future trajectory of AI might look like. Now, when this is gonna be out, like we
mm,
have an internal version that it works, and it I find it like very insightful, but it's a very large body of work. Like this is a very large model that hasn't been thoroughly vetted, and we want to be careful about putting out there things that we're not confident in. So I think it's probably gonna be like at least half a year more before we're ready to share it.
okay, so there's some possibility that we maybe get it by Christmas.
There's some possibility of that, yeah.
All right. Okay. I love timelines forecasting. A through line through many of the things that you said were important open questions was just understanding the impacts of AI. And to me, this is like there's just this key question of like, okay, you can train an AI to a certain loss. What does that mean? You know? So I mean, Epoch has done some work on this just in this like direct approach blog post. I'm wondering what should people read, like what should people look at to get, you know, a good sense of what does loss mean?
Yeah, this is a good question. I think that right now, like I feel I don't have like a good answer to that. So things that have been happening internally at Epoch for us to try to grapple better with this question. Last year, we put out a report on challenges for assessing automation that my colleague David Owen put out, where like he looked at like different work that has been done on like trying to assess like the impact that different AI technologies have had on tasks that are economically useful, and trying to see if there was like a pattern to like which tasks are easier to automate. Like that will be the holy grail for us. Like
Hmm.
having this way of like trying to order like all the tasks that are useful and saying like, well, these are more automatable or like these are less automatable. Like having that kind of notion will be very useful to figure out how AI automation is gonna play out in the future. sadly, the conclusion of that paper is like, work so far, like it hasn't been that good. It disagree, like every single piece that's out there like disagrees with everybody else, and we're just basically very confused about like how to think about automatability and like how we will reach when we will reach different levels of capability in an economically useful sense. One thing that we have started doing recently more within Epoch is our own benchmarking program to try to get like a better sense of like how fast the progress is happening in like different fields, and trying to get a better sense of like, well, if you scale these models, like what should I expect a 10 to a 28 flop model to be able to do? Like
Hmm.
this is to me still like this huge open question where like I don't think anyone has like a really good answer to that just yet.
This is the AI X risk research podcast. A bunch of listeners are like really concerned about X risk from AI, and I think probably a lot of people are concerned that like if we make really good, really smart AI, that might pose an existential risk. Your, Epoch AI in general is a bunch of really smart researchers trying to understand trends in AI progress. Do you think the outputs of your research are going to tell people how to do a good job at making AI? And if so, should people be worried about that?
Sorry, the question is whether the outputs of our work are going to help people, whether this is going to like advance how fast AI is being made.
Yep, that's right.
That's right. So I think that to an extent, this is true. Like having like a better understanding of AI, like naturally, it helps people build better AI. Now, I don't. I think that a lot of the work that we do is things that are already internally known within companies, and I don't imagine that the work that we're doing is being like massively critical for what's been happening at that scale. Now, this is like this is like a hard question you need to grapple with, which is that in the end, like your work is gonna be used in like a multitude of ways, and you don't have like control over that, and you need to be thoughtful about like whether you want to take that trade-off and say like, okay, we're doing this. This might make AI go faster, or like this might make like certain dangers of applications of AI more likely, but then the trade-off is that everyone is going to be like better informed, and we're going to be like better prepared to deal with that situation. It's hard to say. Like also like one thing that I will say is that it's also hard to give an answer to like how fast AI should be going, right? Like
Hmm.
there is a world in which like you want to slow it down, and you want to like, just like have a lot of time to think carefully about how AI is going. But there might be like also a world in which like you want to go quickly over like a period over like a you want to advance quickly up to the point where like you have AI that's going to be really helpful for you to try to improve the way that we align the systems, and we try to help them do our bit in our side. Right now I'm just very confused. So one thing I've been thinking a lot about over the last year is risk evaluation in different contexts, and like trying to think through like different risks. Like I think that the risk on loss of control, that one is more complex to think about, but for the others, like actually right now, like I've been pretty surprised with the uptake of the like how things have played out so far. Like the government seems to be doing like mostly sensible things with like some caveats, but there has been like very reasonable response from thoughtful people to try to anticipate like what's going to happen with AI, like what are the risks that are likely to happen in the next couple of years, and like trying to get ready to act if like something unexpected happens. So in that sense, like I think I've become like, well, seems good for society right now in terms of risk management. Like people seem to be doing like the what will be necessary to manage at least the short term risks about AI. On long term risks, it's like it's so hard to think about, and so some days I wake up thinking like, yeah, maybe having more time and going slowly is gonna be better for society, and other times I'm like, no, actually, like this is a risk that we should take. We should go a bit faster, or like even like if we were right now, we might want to go to get up capabilities like sufficiently high that we can use it to speed up solving this problem and like anything, everything else we deal with.
On this narrow question of just like, is Epoch figuring out any stuff that big labs aren't? One thing that is paying for me here is so when Phil Tetlock is this academic who studies forecasting, and basically study, hey, what if like people actually try to be good at it? Like, I don't know, he gives a bunch more details, but as far as I can tell, the like key criterion is just like, are you actually trying to be good at forecasting? And then everything else sort of flows out from that. Basically, the result is that if people like actually focus on forecasting and get really good at trying, they can do like in forecasting geopolitical questions, they can do like similarly or maybe better, I forget which, than intelligence analysts at, intelligence agencies that, have access to classified details and stuff. Does that suggest that Epoch AI actually is in a position to be better at figuring out AI trends than
To some
big AI
extent,
companies?
I think that this is true. Like, especially like I will even argue that we have one advantage, which is that we're focused on the forest, whereas companies are just focused on the trees. And
Right,
just
right.
having details about the trees is very useful. I would love to have more details about the trees. But if you are the one who's like looking at the big picture and like putting everything together, that gives you like this unique vantage point that others may not have.
Hmm. Yeah, thanks for working in our beautiful backgrounds of our set. 'Cause I believe you're the first guest to do so. Um, yeah. So I guess kind of wrapping up. Are there any questions that I really should have asked but have not?
I'm trying to think how respectably do I want this podcast to end? No, I think that we have covered the basics, and
Okay.
everything that we have covered was like really good. Thank you so much for the
Yeah.
podcast. That was really
Well,
fun. Then
before we do close, people have listened to this. If people are interested in following your research, and your work, how should they do that?
well, first of all, I will welcome everyone to just go right now to their navigation bar and enter epochai.org and just interact with our website. We have lots of resources that I'm sure you're gonna find like very useful. You already mentioned at the beginning of the podcast our trend dashboard. That's where I will start, where you have like all these really important numbers about how fast AI has been developed over the last decade or so. And then we also have like our databases where you're going to be able to see like all these all the data points that make up the trends that we've been studying, and I think will help ground your intuitions about like the massive scale of these models. And of course, like all the research that we put out is publicly in our website. Together with every paper, we try to release a companion blog post which is aimed at less technical audience, and it helps summarize like the main insights of what we found out through our research. So I recommend that people just spend some time going over pages. I think if you're interested in AI, you will find it like a very rewarding experience. Other than that, Epoch AI research is on Twitter, and you can follow us. I'm also on Twitter myself and somewhat active. So if you want to hear more about my hot blistering takes about AI, like I will welcome you to follow me.
Sure. What's Epoch AI's handle on Twitter, and what's your handle on Twitter?
Epoch AI research. That's the handle for Epoch,
Okay.
and mine is J Sevilla Mol.
Okay. Great. Well, yeah, thanks for coming in and thanks for chatting. This has been really fun.
Yes, I can say the same. Thank you so much, Daniel.
This episode is edited by Jack Garrett, and Abra Donace helped with transcription. The opening and closing themes are also by Jack Garrett. Filming occurred at Far Labs. Financial support for this episode was provided by the Long Term Future Fund, along with patrons such as Alexei Malafeyev. To read a transcript of this episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.